Hi, everybody. Thank you very much for having me here, and it's a great honor to present in this session. So I'll be presenting our paper with my fellow PhD student, Paritosh Verma, and our advisor, Psomas. And the title is Automating Food Drop, the Power of Two Choices for Dynamic and Fair Food Allocation. And hopefully, by the end of this talk, the title will make more sense. So let me first start by introducing two major problems, food insecurity and food waste, which hardly need any introduction, but I'll give you some statistics that help highlight the extent of these two problems. So in the US, between 30 and 40% of food is wasted, which is about 149 billion meals yearly. At the same time, almost paradoxically, globally in 2021, 928 million people lived in food insecure households. And in the US specifically, that number is 44.2 million. So there are various organizations, non-profit, that try to address this problem in various scales. One of these organizations is Indie Hunger Network, which has the Food Drop program. And the food drop program used to work as follows. You have a supermarket, and a food delivery is rejected from the supermarket for reasons that have little to do with whether the food is actually edible or not. So the truck driver, instead of throwing this delivery into a landfill, will actually call IHN, and a representative then will start calling one by one available food banks until they find a food bank that will be able to get this delivery, and then they exchange the information between the truck driver and the food bank. So first of all, this procedure was quite labor intensive because they only had one person answering the phone calls, but most importantly, as it happens with human decision making, the decisions were very skewed. Few of the food banks were getting the majority of the donations. So they reached out and they asked us to automate this procedure. So we created a platform, and here you can see a overview of a general use case of the platform that we actually deployed, and it's being used today. And I'll just jump right ahead to present one by one the different steps of a use case. So first of all, a truck driver goes to a supermarket, and the food delivery is going to be rejected at point X. And the truck driver's destination is point Y, which might be the next pickup location or the next delivery or maybe his home. And we also assume that the delivery has a total of W pounds. So the truck driver will go into our platform, and here you can see an actual screenshot of what is being used today. And they will fill in relevant information regarding their contact details, information about the food donation, expected time of departure, and so on. And once they press submit, this will create a request in our backend, which is currently hosted in AWS. And our dynamic and fair matching algorithm will create an ordering of the food banks, and then it will automatically start contacting the food banks one by one. And this is what the food banks see in their end. They get a text message with a link, and if they follow this link, they will see relevant information regarding the donation. And they have the option to either accept or reject the donation. And if they accept, then again, automatically the information of the truck driver and the food bank are being exchanged. So now the truck driver is going to go through the food bank that we matched. The dynamic and fair matching algorithm has some theoretical guarantees, but in order to talk about these guarantees, first I need to theoretically formulate the problem that we have. So we essentially have a graph where each node is being connected by an edge, where the edge has some distance metric. And each node is being characterized by two different things. One is the number of food insecure individuals that reside in this node. And the second one is whether a food bank is open in this specific node or not. In order to prove stuff, we have to make some assumptions, however those assumptions are grounded in real-life practice. The first assumption is that food insecure individuals are being served by the food banks that closest to them. The second assumption is that the food banks distribute uniformly the donations that they get to the food insecure individuals that they serve. And the third assumption is that the weight of the donations will come from some distribution. We can accommodate for any kind of distribution as long as it's somewhat well behaved. We don't want it to have some very heavy tail. And the final assumption is that the origin and the destination of the truck driver is going to be sampled from a distribution that's closely to being proportional to the food insecure population of each node. And this assumption makes sense because the distribution of food insecure individuals follows closely the distribution of people living in each node. And the more people that live in one node, the more supermarkets there, the more food deliveries, the more deliveries are going to be rejected. So, okay, we have defined the problem. What do we want to do? The truck drivers are going to arrive one by one, and we have to immediately and irrevocably match the truck driver to some food bank. And we want the matching algorithm to have two different guarantees. The first guarantee is a driver efficiency guarantee, which we call delta driver efficiency. And here, D is the distance metric. X and Y are the origin and the destination, same as previously. F is the food bank that we choose. And F star is the food bank that minimizes the distance that the truck driver has to drive. So math aside, essentially a matching algorithm that's delta driver efficient will be essentially every truck driver will not have to drive more than delta times their optimal driving distance. So the second guarantee is a fairness guarantee, which we call epsilon multiplicatively envy freeness. And here, WF of M is the weight of food donations food bank F has received after M donations have been delivered. And capital N of F is the food insecure individuals, the number of food insecure individuals that this specific food bank serves. So essentially this ratio is the number, the amount of food, the weight of food that each food insecure individual in food bank F has received. So essentially an epsilon multiplicatively envy-free matching algorithm guarantees that there is no individual that's going to get more than epsilon times the weight of food that some other individual is getting. So let's just jump right ahead to our results. First, I'm going to present some lower bounds. There exists no 3 minus delta driver efficient matching algorithm that's simultaneously better than n multiplicatively envy-free, which essentially means that if you want to be anything better than 3 driver efficient, you're not going to do anything reasonable in terms of the fairness guarantee. And the example is the following, where here nodes V1 through Vn have 1 food insecure individual. There are 0 food insecure individuals in nodes A and B. The red nodes have a food bank. So if you look at the math, essentially the food insecure individual that resides in node V1, his closest, their closest food bank will be in node A. However, in order to be better than 3 minus delta driver efficient, the only way a food delivery can go to node A is if both the origin and the destination are nodes V1, which happens with probability 1 over n squared. However, the amount of food, the amount of deliveries that food bank A should have received is 1 over n. And thus, the n multiplicative envy-freeness is, we get the n multiplicative envy-freeness. And the important thing to stress out here is that this works even in the offline case. Even if we know what's going to happen in the future, this counterexample still holds. So now let's see our results, our algorithms guarantees. And the first thing to say is that our algorithm is pretty straightforward, and this is quite important when you want to implement something in real life practice. So first we find the food bank that's closest to the origin. Then we find the food bank that's closest to the destination. and we give the delivery to the food bank between the two that has received the least amount of weight per food insecure individual they serve. So this matching algorithm is 3-driver efficient and 1 plus epsilon multiplicatively MV free with high probability, where epsilon is something that goes to 0 as the number of food donations go to infinity. So at the end of the day, you cannot hope to do anything better than this given the previous lower bound we discussed. So let's see the analysis on how we would go about proving such a thing. But before doing so, we have to do a quick introduction into randomized processes and specifically balls into bins kind of games. And first consider the following random experiment where I have a total of n bins, and I'll choose one of those bins uniformly at random. And let's say that I choose bin 2, and then I'm going to add a ball in bin 2. Then let's say uniformly at random I chose bin 3, then I'm going to add the ball in bin 3. And I'm going to continue in this way until I add a total of m balls. So now let's consider a second randomized experiment where now I choose 2 different bins uniformly at random, and I'm going to add the ball in the bin that has received the least amount of balls up until that point. So now, since I chose bins 2 and 3, bin 2 has received fewer balls than bin 3, so I'm going to add the ball there, and I'm going to continue this way until adding a total of m balls. And the theoretical question here is, with high probability, what is an upper bound on the number of balls a bin will have at the end of the process? So for the first experiment, the number of balls is going to be m over n, which is the expected number of balls that they're going to have, plus square root m log n over n factor. Now, for the second experiment, the very interesting thing is that when I have 2 choices instead of 1, the extra factor is going to be log n. And the very interesting thing about this is that now the bound does not depend on the number of balls I have inserted. So let's try and see the connection of balls and bins to our setting. So let's consider this graph. And let's assume that the distances of the edges are such that if you are anywhere in the orange area, your closest food bank is the orange food bank. If you are anywhere in the green area, the closest food bank is the green food bank, and so the same for the yellow area. So let's first briefly talk about the 3-driver efficiency. So let's assume that the origin is the green node and the destination is the red node. And let's also assume that the quickest path is this red path. Our algorithm will look at the amount of food that's being donated to the orange food bank and at the amount of food that's being donated at the yellow food bank. And let's assume that we choose the yellow food bank. So this is the route that the truck driver will use. But instead of using this route, they could have chosen to go to the destination using their quickest route, and then go to the yellow food bank and come back. So since this quickest path goes through a food bank, the distance, let's say between, in this particular experiment, between the green food bank and the destination is going to be larger than the distance between the yellow food bank and the destination. So the distance between the destination and the food bank we chose is going to be for sure less than the total distance needed to travel. So the total distance of this path is not going to be more than 3 times the optimal distance. Okay. So I want to circle back to the MV freeness guarantee. Here, essentially, we can think each area as a different bin, where the bins are now going to have some weights. And essentially, since we have an origin and a destination, we pick 2 different bins and allocate the food donation to the bin that has received the least amount of donations up until this point. So the connection to the previous randomized process now becomes more clear. But comparing to the vanilla vanilla to the power of two choices problem, we have some differences. Now, the balls are going to have some weights. Our donations have some weight that comes from some distribution. The food banks are bins that have weights. And the probability of choosing a specific bin is not proportional to its weight, but it comes from some probability that's being close to being proportional. So our contribution to this kind of literature is proving power of two choices style arguments about this setting, which in turn, once we have those, it's pretty easy to show the envy-freeness guarantees of our algorithm. And to finish, I want to present some experiments we did to test also in practice how robust our algorithm is. And so the experiments we conducted were using synthetic data. We chose the nodes of our graph to be the counties of a particular state. We sampled the distance between the counties using the Bing Maps API. The origin and the destination were sampled proportionally to the population of each county. So it wasn't exactly proportional to the food insecure population, but it was almost proportional with some noise. And we used the Feeding America dataset to see how many food insecure individuals reside in each node, the number of individual population that is in each node, and the locations of the different food banks. So we did the experiments for many different states, but I'm just going to present the results for the state of California. And our algorithm is, after 10,000 donations, was 1.0045 multiplicatively envy-free, where 1 is being exactly proportional. And the delta driver efficiency was 2.92, which was very close to the 3 upper bound we have. But the important thing to note here is that on average, the truck drivers didn't need to travel more than 1.06 times their optimal distance. So on average, the driver efficiency was much better than the upper theoretical bound. And to benchmark our results, we compared our algorithm to some natural other matching algorithms. One of them was doing the best for the truck drivers, matching each donation to the food bank that minimizes the driving distance. The other one was doing the best for the food banks, irrespective of how much the truck drivers have to travel. And the third one was one that naturally interpolates between these two extremes, where we do the best for the food banks, but with some specific cutoff where we don't allow for the truck driver to drive more than extra this cutoff. And here you can see for the state of California the results. In the first picture, you see, just for reference, the distribution of food insecure individuals in the state of California. And now in the other 3 images, you see the distribution of food donations in various counties. Red means that this specific county was underserved. Darker color means that it's overserved, and green means that they got approximately the amount of food they should have gotten. So the first is the driver optimal algorithm, which we can see that performs horribly. The second one is our algorithm, which we can see that performs very, very well, as our theoretical results would indicate. And the last one is the greedy with some specific cutoff. And the best for the food banks, of course, will also perform very well in distributing the food evenly, but as we would expect, the results show that the driver efficiency is very bad. So this pretty much wraps up everything. Thank you very much, and I'm here to answer any questions you might have.